In this lesson, we're going to learn how to add, subtract, and multiply radical expressions. We're going to start by learning how to add or subtract radical expressions. In order to add or subtract radical expressions, we need to understand what like radicals are. Like radicals are radicals that have the same index and the same radicand. For example, 2 cubed root of 5 and 8 cubed root of 5 are like radicals. They're like radicals because if you look at their radicals, they have the same index, a 3, and they have the same radicand, 5. I like to think of like radicals as expressions that have the same radical base. Like radicals can have different coefficients. Here the coefficient is a 2, and here the coefficient is an 8. But like radicals must have identical radical bases. These have identical radical bases. They're both the cube root of 5, so we would call these like radicals. 14 square root of z and negative 5 square root of z are like radicals. Notice their radicals have the same index. The index on both of these radicals is a 2, and their radicals have the same radicand. The radicand is a z in both cases. Here's another example of like radicals. They have the same exact radical base, the fourth root of 2x squared. And here's one last example of like radicals. Now, you can only add or subtract radical expressions if they are like radicals. Before we attempt problem 1, we're going to look at a related example. Let's look at this problem here. With expressions involving variables, you can only add or subtract like terms. These are like terms since they have the same variable base. The variable base for both of these is a w. And to add like terms, we keep the variable base, which is a w, and we add the coefficients. So 2 plus 4 will give us 6. If we were to draw this out, what are we actually doing here? Well, we're taking 2 w's and then we're adding 4 more w's. If we take 2 w's and add 4 more w's, we now have a total of 6 w's, which is exactly what we wrote here. Like terms are very similar to like radicals. Just like we can only add or subtract terms if they are like terms, we can only add or subtract radicals if they are like radicals. I've started by copying down this exact original problem, but I've just color-coded it. Now we would say that these are like radicals because they have identical radical bases. The radical base for both of these is the square root of 5x. Since these are like radicals, we can add them. Now to add the like terms, we kept the variable base, which was the w, and we added the coefficients. We do the same when adding like radicals. To add these like radicals, we keep the radical base, which is the square root of 5x, and we add the coefficients. 2 plus 4 will give us 6. Now, to make sense of this, let's draw this out. What are we actually doing here? Well, this means that we have 2 square root of 5x's, and we're adding 4 more square root of 5x's. And if we take 2 square root of 5x's and add 4 more square root of 5x's, we now have a total of 6 square root of 5x. Let's take a look at this next example. These are like radicals since they all have the same radical base. The radical base here is the cube root of 11. So since these are like radicals, we can add or subtract them. And to do that, we're going to keep the radical base, which is the cubed root of 11, and then we'll add or subtract the coefficients. Now the coefficient on this radical is not written, so the implied coefficient is a 1. So we'll take 5 minus 8 to get negative 3, and negative 3 plus 1 will give us negative 2. Now for this example here, we have to look carefully. Are all of these like radicals? No, they are not. Because remember, with like radicals, the radicals must have the same index and the same radicand. To start, these are like radicals because they both have the same radical base, the square root of 7. So we can combine these like radicals. And to do that, we keep the radical base, which is the square root of 7, and we'll subtract the coefficients. 12 minus 3 will give us 9. Then these are like radicals because they have the same radical base, the fourth root of 7. So we can add these like radicals. And to do that, we keep the radical base, which is the fourth root of 7, and we'll add the coefficients. 5 plus 6 will give us a positive 11. And you can write these terms in either order. You could instead put the 11 4th root of 7 first and the 9 square root of 7 second. Now, these are not like radicals. This has a radical base of the square root of 20, and this has a different radical base, the square root of 45. So as written, we cannot add these radicals. But notice both of these radicals can be simplified. So let's simplify first, and maybe after simplifying, we will then have like radicals. I'm going to simplify 3 square root of 20 in purple over here, and I'll simplify 8 square root of 45 in green over here. Now, if you'd like an introduction and detailed overview of how to simplify radicals, please watch my 6.3 video. Since we're dealing with square roots here, we're looking for perfect squares underneath the radical. To start, 20 is not a perfect square. If we look at the list of perfect squares in our 6.3 worksheet, 20 is not on this list. So since 20 is not a perfect square, we need to find the largest perfect square that multiplies evenly into 20. To do that, we start with the largest number on the list that's less than 20, because in order to multiply into 20, it has to be less than 20. That would be 16. Does 16 multiply evenly into 20? No, because 20 divided by 16 gives us a decimal. Let's work our way down. Does 9 multiply evenly into 20? No, because 20 divided by 9 gives us a decimal. Does 4 multiply evenly into 20? Yes, it does, because 20 divided by 4 gives us a nice whole number. So 4 is the largest perfect square that multiplies evenly into 20. So we need to rewrite 20 as 4 times some number. And 20 can be rewritten as 4 times 5. And I'm always going to put our perfect powers in red. Now that we've identified our largest perfect square, we want to write it as some quantity squared. So I'm going to rewrite 4 as 2 squared, and 5 is not a perfect square, it's just the leftover after we pulled out the largest perfect square 4. So I'm just going to carry down our 5. Now, in my 6.3 video, we learned that when you have a square root, anything underneath the radical that has a 2 for an exponent can be pulled out of the radical. So we can pull this 2 out of the radical. That will leave us with our coefficient 3 times the 2 that we're pulling out. Now, why can we pull the 2 out of the radical? Well, let's focus all of our attention on the square root of 2 squared. The square root and the square are inverse operations. So the square root on the 2 is canceled by the square on the 2, just leaving us with 2. Now let's focus all of our attention on the square root of 5. This 5 does not have a 2 for an exponent, so there's no square exponent to cancel the square root, so that means the 5 stays underneath the square root symbol. And we can simplify this by multiplying the 3 times the 2 to give us 6 square root of 5. Now that we've simplified 3 square root of 20 to 6 square root of 5, next let's simplify 8 square root of 45. Since we have a square root here, we're looking for perfect squares underneath the radical. 45 is not a perfect square, so we need to find the largest perfect square that multiplies evenly into 45. If you look at our list of perfect squares, you'll find that 9 is the largest perfect square that multiplies evenly into 45. So we need to rewrite 45 as 9 times some number, and 45 can be written as 9 times 5. Now that we've identified our largest perfect square, we can write 9 as 3 squared, and 5 was just the leftover after pulling out the largest perfect square, so we'll just keep bringing down the 5. Now, since this is a square root, anything underneath the radical that has a 2 for an exponent can be pulled out of the radical. So we can pull the 3 out of the radical, and that will leave us with our coefficient 8 times the 3 that we're pulling out, and since the 5 does not have a 2 for an exponent, it stays underneath the radical. And we can simplify this by multiplying 8 times 3 to get 24 square root of 5. Now that we've simplified, we have like radicals. They both have the same radical base, the square root of 5. So since these are like radicals, we can add them. To add like radicals, we keep the radical base, which is the square root of 5, and we add the coefficients. 6 plus 24 will give us 30. Let's take a look at this last example over here. Notice these are not like radicals. They have different radical bases. Since these are not like radicals, they cannot be subtracted. But let's check to see if we can simplify, because sometimes if you simplify first, you will then end up with like radicals, like we did over here. Now, since these are square roots, we're looking for perfect squares underneath the radicals. 10 is not a perfect square, And if you look at our list of perfect squares, you will find that there are no perfect squares other than one that multiply evenly into 10. So that means that the square root of 10 cannot be simplified. 3 is not a perfect square, and there are no perfect squares other than one that multiply evenly into 3. So that means the square root of 3 also cannot be simplified. So these are not like radicals, and they can't be simplified, so we cannot subtract these radical expressions. Let's take a look at this next example. Remember, you can only add or subtract radicals if they are like radicals. These expressions are not like radicals because they have different radical bases. So as written, we cannot add or subtract these radicals. Let's try simplifying them. Maybe after we simplify these radicals, we will have like radicals. I'm going to simplify this first radical in purple, this second radical in green, and this third radical in blue. To simplify this first radical, let's first notice that we're dealing with a square root, so that means that we're looking for perfect squares. 98 is not a perfect square. If you look at our list of perfect squares, you'll find that 49 is the largest perfect square that multiplies evenly into 98. So let's rewrite 98 as 49 times 2. Next, we need to look at the variable. And remember, since this is the square root, we're looking for perfect squares. So first we ask ourselves, is x cubed a perfect square? If we look at page 7 of our 6.3 worksheet, there we made a list of variables that are perfect squares, perfect cubes, and perfect fourths. We'll focus on the perfect squares column. We're trying to determine if x cubed is a perfect square. X cubed is not on this list, so that means that x cubed is not a perfect square. But even if you don't have this list in front of you, you can quickly identify perfect squares. A variable is a perfect square if its exponent is a multiple of 2. X cubed is not a perfect square since the exponent 3 is not a multiple of 2. To find the largest perfect square that multiplies evenly into x cubed, the trick that we learned is to look for the exponent as close as we can possibly get to 3, but it has to be less than 3. That exponent would be a 2. That means that the largest perfect square that multiplies evenly into x cubed is x squared. So we need to rewrite x cubed as x squared times some quantity, and x cubed can be rewritten as x squared times x, because remember our rules of exponents say that when you multiply two quantities with the same base, we keep the base and add the exponents. So 2 plus this exponent 1 would give us our x cubed. If we look at this middle term here, 3 is not a perfect square, and there are no perfect squares that multiply evenly into 3. So we can't simplify the square root of 3. Same with the x. X is not a perfect square, and there are no perfect squares that multiply evenly into x. So this expression here cannot be simplified any further, so I'm just going to carry it down. Next, let's look at this expression here. 300 is not a perfect square. The largest perfect square that multiplies evenly into 300 is 100. So let's rewrite 300 as 100 times 3. And now we see x cubed again, just like we did over here. We already determined that the largest perfect square that multiplies evenly into x cubed is x squared. So just like we did over here, let's rewrite x cubed as x squared times x. Now that we've identified all of the largest perfect squares in red here, anything underneath the radical that's a perfect square, we need to write it as some quantity squared. So let's write 49 as 7 squared. X squared is already perfectly written as some quantity squared, so we'll just leave it as x squared. We said that this radical can't be simplified, so I'm going to just keep carrying it down. And in this radical, let's rewrite 100 as 10 squared. Now we've written all of the perfect squares in red as some quantity squared. Our next step, anything underneath the radical that has a 2 for an exponent can be pulled out of the radical. So in this first radical, we'll pull out the 7 and we'll pull out the x. This 2 and this x do not have a 2 for an exponent to cancel the square root, so these are left underneath the square root symbol. And we'll continue to carry this expression down. And for this radical, we'll start by carrying down the coefficient, and when we bring out the 10, we'll multiply it by this existing coefficient, and then we'll bring out the x as well. All that we're left with underneath the radical is 3 and x. Now, for this radical expression here, let's just multiply these coefficients here, and negative 7 times 10x will give us negative 70x. Now we've taken each radical and simplified it as much as we can. Now let's see if we can add or subtract these radicals. These two radicals are like radicals because they have the same radical base. Their radical base is the square root of 3x. This is not a like radical because its radical base is different. It's the square root of 2x. So we cannot add this radical to the other two. So I'm just going to carry this radical down for our answer. To subtract these radicals, we'll keep the radical base, which is the square root of 3x. And then 2x minus 70x will give us negative 68x. And so this is our final fully simplified answer. Let's take a look at this example here. Again, as written, these are not like radicals. They have different radical bases, so we cannot add these radicals together. Let's start by simplifying because maybe after we simplify, then we'll have like radicals. I encourage you to pause the video and try the next two problems on your own and then play the video to check your answer. I'm going to simplify this radical in purple, this radical in green, and this radical in blue. Now let's first recognize that the index here is a 3, so that means we're looking for perfect cubes underneath the radicals. 135 is not a perfect cube. 27 is the largest perfect cube that multiplies evenly into 135. Therefore, let's rewrite 135 as 27 times 5. Next, we need to ask ourselves, is x to the fourth a perfect cube? It is not, and we know that because a variable will be a perfect cube if its exponent is a multiple of 3. 4 is not a multiple of 3, so that means that x to the fourth is not a perfect cube. If we look at our list on page 7 of our 6.3 worksheet, here we made a list of variables that are perfect cubes. To find the largest perfect cube that multiplies evenly into x to the fourth, all we need to do is find the exponent as close to 4 as we can possibly get, but it has to be less than 4. It looks like that exponent would be 3, so our largest perfect cube that multiplies evenly into x to the fourth is x cubed. So we need to rewrite x to the fourth as x cubed times some quantity. And x to the fourth can be written as x cubed times x, because if we add these exponents, the 3 plus the 1 will give us 4. Next, let's look at this middle expression here. 5 is not a perfect cube, and there are no perfect cubes other than 1 that multiply evenly into 5. So we can't simplify the cubed root of 5, and same with x. X is not a perfect cube, and there are no perfect cubes that multiply evenly into x. So that means that this radical cannot be simplified any further. So I'm just going to carry this down here. Next, let's look at this radical in blue. 40 is not a perfect cube. 8 is the largest perfect cube that multiplies evenly into 40. So let's rewrite 40 as 8 times 5. Now let's look at the variable x. X is not a perfect cube, but there are no perfect cubes that multiply evenly into x. So x can't be simplified, we'll just leave it as is. Now that we've identified all of our largest perfect cubes in red, anything that's a perfect cube underneath the radical, we need to write it as some quantity cubed. 27 can be written as 3 cubed. X cubed is already written perfectly as some quantity cubed, so we'll leave it. We said that this middle radical can't be simplified any further, so we're going to bring it down. And for this radical here, 8 is a perfect cube, so let's rewrite it as 2 cubed. Now that we've identified all of the largest perfect cubes, and we've written those perfect cubes as some quantity cubed, now we can pull those perfect cubes out of our radical. Let's pull out the 3 and the x here. That will leave us with the negative 3 and the x that we're pulling out. And underneath the radical, we're left with 5x. This green radical expression couldn't be simplified, so we'll just carry it down. And for this radical here, we'll pull the 2 out of the radical. That will leave us with the 2 that we're pulling out times the coefficient x. And all that's left underneath the radical is 5x. Now, we've simplified these radicals as much as we possibly can. Now, let's see if we can add them. we'll be able to add them if they're like radicals. Let's see. This radical base is the cubed root of 5x. This radical base is the cubed root of 5x. And this radical base is the cubed root of 5x. These three expressions have the same radical base, so that means they are like radicals. We can add them. When adding like radicals, we keep the radical base, which is the cubed root of 5x, and we add the coefficients. Let's see, negative 3x plus 4x will give us 1x, and 1x plus 2x will give us 3x. For this example, remember, we can only add or subtract radicals if they are like radicals. These are not like radicals since they have different radical bases. So let's first simplify, because maybe after simplifying, we'll then have like radicals. I'm going to simplify this radical in purple here. I'll simplify this radical in green, and I'll simplify this radical in blue. Let's start with this radical here. Notice we're dealing with the cubed root, so that means we're going to be looking for perfect cubes underneath our radical. Let's first ask ourselves, is 64 a perfect cube? It is. If you look at our list of perfect cubes from our 6.3 worksheet, you'll find 64 on that list. So for now, I'm just identifying the perfect cubes. Since 64 is a perfect cube, I'm going to put it in red. Next, let's look at our variable. Is a to the fifth a perfect cube? It is not, because remember, variables that are perfect cubes always have an exponent that is a multiple of 3. 5 is not a multiple of 3, so a to the fifth is not a perfect cube. A cubed is the largest perfect cube that multiplies evenly into a to the fifth. So let's rewrite a to the fifth as a cubed times a squared, since if we add the exponents, 3 plus 2, we get 5. Next, let's focus on this radical in green. We're looking for perfect cubes. Is negative 8 a perfect cube? It is. So for now, I'm just identifying the perfect cubes. Since negative 8 is a perfect cube, I'm going to put it in red. A squared is not a perfect cube since the exponent 2 is not a multiple of 3. There are no perfect cubes that multiply into a squared. So that means that a squared can't be simplified. We will just leave it as is. Next, let's focus on this radical here. Is 343 a perfect cube? It is. If you look at our list of perfect cubes, you'll find 343 on that list. You'll also know that these are all perfect cubes because if you take the cubed root of 64 or the cubed root of negative 8 or the cubed root of 343 on your calculator will give you a whole number. So 343 is a perfect cube, so I'm just going to put it in red for now. Again, like we said over here, a squared is not a perfect cube, and there are no perfect cubes that multiply evenly into a squared. So we'll just leave a squared as is. Now that we've identified all of our perfect cubes in red, we want to write each of those perfect cubes as some quantity cubed. 64 can be written as 4 cubed. Negative 8 can be written as negative 2 cubed. And 343 can be written as 7 cubed. Now that we've identified all of our largest perfect cubes and we've written them all as some quantity cubed, now, since these are cubed roots, anything underneath the radical that has a 3 for an exponent can be pulled out of the radical. So for this first radical, we'll pull out the 4 and we'll pull out the a, and all that's left underneath the cubed root is a squared. For this radical here, we can pull out the negative 2, and that will leave us with negative 5a times the negative 2 that we're pulling out, and all that's left underneath the cubed root is a squared. Finally, for this radical here, we can pull out the 7, and that will leave us with the 7 that we're pulling out, and underneath our cubed root, we'll be left with a squared. Now we're almost completely simplified, but I notice that I can multiply negative 5a times negative 2 to get a positive 10a. Now we've simplified each of these radicals completely. Now let's see if we have any like radicals that can be added. To start, I notice that these are like radicals. They both have identical radical bases, so to add them, we keep the radical base, which is the cubed root of a squared, and we add the coefficients. 4a plus 10a will give us 14a. Now we added these together to get this expression. Now this also has the same radical base, the cubed root of a squared. So these are like radicals. But notice, to add these like radicals, we would keep the radical base and add the coefficients, but 14a and 7 are not like terms. They can't be added. So since we can't add these coefficients, we can write our final answer in two ways. We can either just bring down this term here and write this as our final answer, because again, while these are like radicals, their coefficients can't be added since their coefficients are not like terms. But there is another way we could write our final answer here. Again, these are all like radicals, so to add them, we keep the radical base, which is the cubed root of a squared, and then our new coefficient is the sum of these three coefficients. So let's see. If we take 4a plus 10a, we get 14a, and 14a plus 7 is just 14a plus 7. We can't simplify that any further. So our new coefficient can be written as 14a plus 7. And we need to put this in parentheses to make sure that the radical base is applying to this whole coefficient. So you can write your final answer in either form. Both of these will be accepted. Now that we've practiced adding or subtracting like radicals, we're going to look at how to multiply radicals. We're going to start by doing this a longer way, and then I'll talk about a shortcut down here. Notice we can use the distributive property here. Let's start by distributing the square root of 2 to the square root of 2, which will leave us with the square root of 2 times the square root of 2, and then we'll distribute the square root of 2 to the square root of 26 to leave us with a positive square root of 2 times the square root of 26. Now, in chapter 6.3, we learned the product property of radicals. The product property of radicals says that when you're multiplying two radicals that have the same index, you can combine that multiplication underneath one radical symbol to give us the square root of 2 times 2. Let's use the product property of radicals over here as well. Since we're multiplying two radicals with the same index, we can combine that multiplication underneath one square root symbol to give us the square root of 2 times 26. Now, the square root of 2 times 2 simplifies to the square root of 4, and if we multiply 2 times 26, that will give us the square root of 52. Now, we're trying to add these two radicals, but these are not like radicals, so they cannot be added. If they're not like radicals, check to see if you can simplify. And with radicals, you always want to simplify them if you can. The square root of 4 simplifies to 2. 52 is not a perfect square. So to simplify this, we need to find the largest perfect square that multiplies evenly into 52. 4 is the largest perfect square that multiplies evenly into 52. So let's rewrite 52 as 4 times 13. Now, I've written 4 as 2 squared, and now we can pull the 2 out of the radical. That will leave us with this 2 plus the 2 that we're pulling out, and 13 is left underneath the square root symbol. Now that we've simplified these radicals, can we add these expressions? No, these are not like radicals. This has a radical base of the square root of 13, and this has no radical base. So these are not like radicals. If we briefly look at a related example, these are not like terms, since this has x as its variable base, and this has no variable base, so we cannot add them. Similarly, these are not like radicals, since this has square root of 13 for its base, and this does not have any radical base. So since these are not like radicals, we cannot add them. So this cannot be simplified any further. This is our final fully simplified answer. Now, we could have actually used a shortcut here. When you multiply two identical square roots, there's a nice shortcut you can use. Before I tell you the shortcut, let's look at some quick examples. If we're multiplying the square root of 5 times the square root of 5, the product property of radicals says we can combine that multiplication underneath one square root symbol, which would give us the square root of 5 times 5, which equals the square root of 25, and the square root of 25 is equal to 5. Let's look at another example. To multiply the square root of 10 times the square root of 10, we can combine that multiplication underneath one square root symbol to give us the square root of 10 times 10, which simplifies to the square root of 100, and the square root of 100 is 10. Now, do you notice a pattern here? The square root of 5 times the square root of 5 is equal to 5. The square root of 10 times the square root of 10 is equal to 10. So, hopefully you're noticing a pattern here. What do you think the square root of 1,768 times the square root of 1,768 is? That would be 1,768. So the shortcut here is when you multiply two identical square roots, your answer will just be the radicand, which is 5 in this case, or 10 in this case. So we could have used the shortcut up here. Notice we were multiplying two identical square roots here, And so the square root of 2 times the square root of 2 is just equal to 2. We could have jumped from this step to this step without having to go through these intermediary steps. Now I want to be very clear here. This shortcut only works when you're multiplying two identical square roots. It does not work when the index is anything other than a 2. For example, the shortcut doesn't work with cubed roots or fourth roots or fifth roots, etc. So the square root of 8 times the square root of 8 would equal 8. But the cubed root of 8 times the cubed root of 8 does not equal 8. We can compute this the longer way and see that this in fact does not equal 8. To compute the cubed root of 8 times the cubed root of 8, the product property of radicals says we can combine that multiplication underneath one radical symbol, which would give us the cubed root of 8 times 8, and 8 times 8 will give us the cubed root of 64, and 64 is a perfect cube. We can rewrite 64 as 4 cubed, and then the cubed root and the cube cancel each other out, and we're just left with our final answer, 4. So we can see here this does not equal 8. The product property of radicals gives us the correct answer of 4. So make sure you only use this shortcut with square roots. Let's take a look at another example. Let's again use the distributive property here. First, we'll multiply the cubed root of 9 times the cubed root of 5. Then when we distribute here, we're multiplying a positive number times a negative number, and a positive times a negative will give us a negative. And let's see, we're multiplying the cubed root of 9 times the cubed root of 18. Here, since both of these radicals have the same index, we can combine that multiplication underneath one radical symbol. So that will give us the cubed root of 9 times 5. Same thing here, since we're multiplying two cubed roots, we can combine that multiplication underneath one radical symbol to give us the cubed root of 9 times 18. And if we multiply 9 times 5, that will give us the cubed root of 45, and 9 times 18 will give us the cubed root of 162. Now we have a subtraction problem. And remember, you can only add or subtract radicals if they are like radicals. These are not like radicals, and they need to be simplified. So let's go ahead and simplify them. 45 is not a perfect cube. And if you look at your list of perfect cubes, there are no perfect cubes other than one that multiply evenly into 45. So that means the cubed root of 45 cannot be simplified, so I'm just going to carry it down. 162 is not a perfect cube, so we need to find the largest perfect cube that multiplies evenly into 162, and that would be 27. So let's rewrite 162 as 27 times 6. Now, 27 is our perfect cube, so we need to write it as some quantity cubed. So all I've done in this step is just rewrite 27 as 3 cubed. Now, since we're dealing with cubed roots, anything underneath the radical that has a 3 for an exponent can be pulled out of the radical. Let's pull out this 3. That will leave us with the 3 that we're pulling out, and underneath the cubed root, we'll still have 6. You always want to simplify radicals if you can, and we've simplified, but now we need to ask ourselves, can we subtract these? We cannot, because these are not like radicals even after simplifying. So this is our final answer. We can't simplify any further. Now before we take a look at these next two examples, it's important to know the distinction between adding and subtracting radicals and multiplying radicals, because it's easy to confuse the two. You can only add or subtract radicals if they are like radicals. To add or subtract like radicals, we add or subtract the coefficient and we keep the same radical base. Let's look at two examples. These are like radicals since they have the same radical base, the square root of 6. So since these are like radicals, we can add them. And to add these, we keep the radical base, which is the square root of 6, and we add the coefficients. 2 plus 5 will give us 7. These are not like radicals because they do not have the same radical base. This radical base is the cubed root of 2, and this radical base is the cubed root of 7. Check to see if you can simplify the radicals, but we can't, so that means that we cannot add these radicals. They're not like radicals. Let's compare that to multiplying radicals. We can multiply any radicals as long as they have the same index. And to multiply radicals, we multiply the coefficients and we multiply the radicals. So let's look at two examples. Both of these radicals have an implied index of a 2. So they have the same index, we can multiply them. And remember, when you multiply like quantities. So I'm going to break this apart into separate pieces. And remember, with multiplication, you can use the commutative property and rearrange the pieces however you'd like. So since we multiply like quantities, I'm going to put the like quantities next to each other. 2 and 5 are numbers, they're like quantities. So I've put them next to each other. And the square root of 6 and the square root of 6 are both radicals, so we'll consider them like quantities. So I've put them next to each other. Now let's multiply the like quantities. 2 times 5 will give us 10, and to multiply the square root of 6 times the square root of 6, the product property of radicals says when you're multiplying two radicals, as long as they have the same index, you can combine that multiplication underneath one radical symbol. So that would give us the square root of 6 times 6, which would simplify to the square root of 36. And the square root of 36 is just 6, so this would simplify to 10 times 6. And 10 times 6 will give us our final answer, 60. Now we could have used a shortcut here, because remember, when you multiply two identical square roots, your answer is just the radicand. So the square root of 6 times the square root of 6 just gives us 6. We could have jumped from here right down here. Let's take a look at this last example here. Notice we could not add 4 cubed root of 2 plus 8 cubed root of 7 because they're not like radicals. But we can multiply them, because to multiply radicals, all that you need is for them to have the same index. Both of these radicals have the same index, a 3 in this case. Since they have the same index, we can multiply them. So you multiply the coefficients and you multiply the radicals. Let's start by multiplying the coefficients. 4 times 8 will give us 32. And then let's multiply the radicals. We can multiply these radicals since they have the same index. The product property of radicals says we can combine this multiplication underneath one cubed root symbol. So that will give us the cubed root of 2 times 7. And this will simplify to the cubed root of 14. Now, whenever you have a radical for your final answer, you always want to check to see if you can simplify it. But 14 is not a perfect cube, and there are no perfect cubes that multiply evenly into 14. So this cannot be simplified any further. Here's an example of radicals that cannot be multiplied. The index here is a 3 and the index here is a 4. So these radicals cannot be multiplied because the index is different. Let's use this information now for these next two examples. For this expression here, we're going to FOIL. Let's start by multiplying the first. 5 times 3 will give us 15. Then we'll do the outer, and we'll take a positive 5 times 2 square root of 7. Then we'll take the inner, so we'll take negative 4 square root of 7 times 3. And then we'll take the last, which will give us negative 4 square root of 7 times 2 square root of 7. Now we need to simplify, and let's take each of these colored quantities separately. 15 is as simplified as it can get, so we'll just bring it down. Now if we look at this green quantity, we're multiplying. Remember, when multiplying, you multiply the coefficients and you multiply the radical. That's because we multiply like quantities. The numbers or the coefficients are like quantities, so we multiply. 5 times 2 will give us 10. And there's no other square root here, so there's nothing to multiply the square root of 7 by. So we leave the square root of 7 as is. Next, let's look at this quantity in orange. Remember, when you're multiplying, you multiply the coefficients and you multiply the radicals. So if we take negative 4 times 3, that will give us negative 12. And there's no other square root here, so there's nothing to multiply the square root of 7 by, so we'll just leave it as a square root of 7. Next, let's look at this quantity in blue. Remember, when you're multiplying radicals, you multiply the coefficients and you multiply the radicals. So let's multiply the coefficients. Negative 4 times 2 will give us negative 8. And we'll talk about the shortcut for multiplying these radicals in just a minute, but let's use the longer product property for now. So to multiply two square roots, the product property says that we can combine that multiplication underneath one radical symbol to give us the square root of 7 times 7. Now, these are fully simplified, so I'm just going to carry these three terms down as they are. But here, let's go ahead and multiply 7 times 7 to leave us with negative 8 square root of 49. Now again, these can't be simplified any further, so I'm going to keep carrying them down. But 49 is a perfect square. The square root of 49 gives us 7. So this can be simplified to negative 8 times 7. Now, we could have actually used a shortcut to skip directly from this step to this last step here. Here we're multiplying the square root of 7 times the square root of 7, And we know that when you multiply two identical square roots, the answer is just the radicand. So the square root of 7 times the square root of 7 will just give us 7. So we could have just jumped from this step down here. Now, to further simplify this, I'm just going to take -8 times 7 to get -56. Now, I've been focusing on simplifying each individual term, but now let's look at the expression as a whole. To start, we can take 15 minus 56 to get -41. And now, can we subtract these radicals? Well, you can only add or subtract radicals if they are like radicals. These are like radicals since they have identical radical bases, the square root of 7. So we can subtract these like radicals, and to add or subtract like radicals, you add or subtract the coefficient and keep the same radical base. So we'll keep the radical base, which is the square root of 7, and we'll take the coefficient 10 minus the coefficient 12 to get -2. Now, can we simplify any further? Well, you always want to look at the radicals in your final answer to see if those radicals can be simplified. The square root of 7 cannot be simplified since there's no perfect squares that multiply evenly into 7. Also, can we combine these terms? No, because these are not like radicals. This has a radical base of the square root of 7, and this has no radical base at all. So these are not like radicals, they can't be subtracted. So this is our final fully simplified answer. Usually, when you have two terms for your final answer, if one of the terms has a radical base and the other term does not, standard notation in textbooks is usually to write the term with the radical base last, like we did here. But if you switched these around and wrote the term with the radical first and the constant last, that would still be correct. Let's take a look at the next example. Now be very careful here because there's a very common mistake that happens for problems like these. It's very tempting to distribute this exponent, but exponents do not distribute across addition or subtraction. So if you tried to distribute the 2 to the square root of 5 to get the square root of 5 squared, and then distribute the 2 to the square root of 3 to get the square root of 3 squared, you will not get the correct answer. This is not mathematically equivalent to this. If you were to type this expression into your calculator, you'll get a decimal. And if you were to type this expression into your calculator, you'll get a different decimal because these are not equivalent. So do not distribute exponents across addition or subtraction. The correct way to solve this is to rewrite this quantity squared as the square root of 5 plus the square root of 3 times itself, the square root of 5 plus the square root of 3. Now, we're going to want to FOIL again. We'll start by multiplying the first, so we'll take the square root of 5 times the square root of 5. Then we'll multiply the outer, so we'll take the square root of 5 times the square root of 3. Then we'll multiply the inner, so we'll take the square root of 3 times the square root of 5. And then we'll multiply the last, so we took the square root of 3 times the square root of 3. Now let's focus on simplifying this piece, this piece, this piece, and this piece. Remember, you can multiply radicals as long as they have the same index. These are both square roots, so we can multiply them. These are both square roots, so we can multiply them. These are square roots, and these are square roots. So it looks like we'll be able to multiply each of these pairs of radicals. And let's use the product property of radicals here. The product property of radicals says when you multiply two radicals with the same index, you can combine that multiplication underneath one radical symbol. So this will give us the square root of 5 times 5. This can be rewritten as the square root of 5 times 3. This can be rewritten as the square root of 3 times 5. And this can be rewritten as the square root of 3 times 3. This will simplify to the square root of 25. This will simplify to the square root of 15. This will also simplify to the square root of 15. And this will simplify to the square root of 9. Now 25 is a perfect square, so the square root of 25 simplifies to 5. 15 is not a perfect square, and there's no perfect squares that multiply evenly into 15. So this radical cannot be simplified. We'll just carry it down. And we'll carry down this square root of 15 as well. And the square root of 9 simplifies to a positive 3. Now notice we could have used our shortcut in two places here. Here we multiplied two identical square roots, and so the answer is just our radicand. The square root of 5 times the square root of 5 gives us 5. Here these square roots were different, so we couldn't use our shortcut. Here the square roots were different, so we couldn't use our shortcut. But here again, we're multiplying two identical square roots. Our shortcut tells us that the square root of 3 times the square root of 3 is just equal to 3. Now we've simplified each of these individual pairs of radicals. Now let's look at this expression as a whole and see if we can further simplify it. Well, we can add like terms or like radicals. So let's start by adding the 5 and the 3 to get 8. Now I want to take a closer look at the square root of 15 plus the square root of 15, because this is where a lot of mistakes happen. When we're multiplying radicals, we can always use the product property of radicals, which says as long as you're multiplying two radicals with the same index, you can combine that multiplication underneath one radical symbol, like this. And this would simplify to the square root of 100, which would simplify to 10. We of course could have used our shortcut here as well, which says when you're multiplying two identical square roots, the answer is just the radicand 10. Now, this is how we multiply radicals. Adding and subtracting radicals is different, but a lot of people will mistakenly try to add radicals the same way that we multiply radicals. So a lot of people will say, okay, let's combine this addition underneath one radical symbol like this, and that will give us the square root of 20. This is not mathematically correct. If you were to take on your calculator the square root of 10 plus the square root of 10, you'll get a decimal. And if you type the square root of 20 into your calculator, you'll get a completely different decimal. This is not equivalent to this. This is not the strategy we use to add radicals. Remember, you can only add radicals if they are like radicals. These are definitely like radicals since they're identical. Now, to add like radicals, we keep the radical base, which is the square root of 10 in this case, and we add the coefficients. The implied coefficient here is a 1, and the implied coefficient here is also a 1. So if we take 1 plus 1, that will give us 2 square root of 10. And that makes sense. If you have 1 square root of 10, and you add another square root of 10, we now have 2 square roots of 10. So now, we can add these radicals because they are like radicals. And when we add radicals, we keep the radical base, which is the square root of 15, and we add their coefficients. The implied coefficient on this is a 1, and the implied coefficient here is a 1 as well. So if we take 1 plus 1, that will give us a positive 2. Now, 8 and 2 square root of 15 are not like radicals or like terms. They can't be combined any further because this has a radical base and this number does not. Let's take a look at these last two examples. Now notice these examples are a special case because what's inside the parentheses looks identical. We have a square root of 8 and a 5. The only difference is that one parenthesis has a minus and the other has a plus. That's the same case here. What's inside the parentheses looks identical. We have a 6 and a 6 and a 4 square root of 3 and 4 square root of 3. The only difference is that one has a plus and one has a minus. You can always FOIL for situations like this, but when you have that special case where what's inside the parentheses looks identical, but one has a plus and one has a minus sign, instead of FOILing, we could use the difference of two squares formula. So we'll practice both approaches. Let's start by FOILing. And I started by copying this exact expression right here. We'll multiply the first to get the square root of 8 times the square root of 8. Then we'll multiply the outer to get 5 times the square root of 8. Then we'll multiply the inner to get negative 5 times the square root of 8. And then we'll multiply the last to get negative 25. Now notice here we're multiplying two identical square roots. So we can use the shortcut here. The square root of 8 times the square root of 8 will give us 8. Now, these are like radicals. They both have identical radical bases, which is the square root of 8. So we can subtract these like radicals. And notice these like radicals will cancel out. 5 square root of 8 minus 5 square root of 8 gives us 0 square root of 8, which is equal to 0. And then I'll bring down the minus 25. And then we can compute 8 minus 25 to get our final answer of negative 17. Let's FOIL this expression down here, and then we'll look at the difference of two squares formula. I've started by copying down this exact original problem here, and to FOIL, we'll take 6 times 6 to get 36, then we'll multiply the outer, and for now I'm just going to write that as a positive 6 times negative 4 square root of 3. Then we'll multiply the inner, and again for now I'm just going to write this as a positive 4 square root of 3 times 6, and then we'll multiply the last. So we'll take a positive 4 square root of 3 times negative 4 square root of 3. Now let's simplify. We'll bring down the 36. Now if we look at this quantity in green, when you're multiplying quantities, we multiply like quantities. So we multiply any coefficients. 6 times -4 will give us -24. And we multiply any radicals. Well, there's no other radical to multiply this square root of 3 by, so we'll just bring down the square root of 3. We'll do a similar thing here. We multiply the like quantities, so we'll take 4 times 6 to get a positive 24, and there's no other square root to multiply by this square root of 3, so we'll just carry down the square root of 3. And in blue here, when we're multiplying quantities, we multiply the like quantities. So we multiply the coefficients, and we multiply the radicals. 4 times -4 will give us -16. And here, since we're multiplying two identical square roots, we can use our shortcut. The square root of 3 times the square root of 3 will give us 3. Now, these are like radicals because they have the same radical base. And notice these like radicals will cancel out because when you take -24 square root of 3 plus 24 square root of 3, you get 0 square root of 3, or in other words, 0. So when we cancel these out, we're left with 36, and -16 times 3 will give us a -48. And 36 minus 48 simplifies to -12. So foiling will get us the correct answer here. But remember, when you have this special situation where what's inside your parentheses is identical, the only difference is that one has a minus and one has a plus sign, you could use the difference of two squares formula instead of foiling. Let's quickly review the difference of two squares formula. You can use the difference of two squares formula anytime your parentheses look identical, but one has a plus and one has a minus sign. The difference of two squares formula says, just take the first quantity, x, and square it, then take the second quantity, 9, and square it, and then put a minus sign in the middle. And then if we simplify, this would give us x squared minus 81. So we're going to use this difference of two squares formula to solve our last two problems. The difference of two squares formula says when you multiply two parentheses that look identical, but one has a plus and one has a minus sign, your answer will be a squared minus b squared. So I started by copying down this exact original problem here to use the difference of two squares formula here. We'll take this quantity and square it, and then we take this quantity and square it, and then we always put a minus sign in the middle. That's why it's called the difference of two squares, because you're subtracting two squares. What does this simplify to? Well, the square root and the square are inverse operations. They cancel each other out. So the square cancels the square root, and we're just left with 8. Another way to think about this is that the square root of 8 squared is equal to the square root of 8 times the square root of 8. And we know that when we're multiplying two identical square roots, the square root of 8 times the square root of 8, that just gives us 8. And then 5 squared will give us 25, so we'll be left with 8 minus 25, which gives us -17. Notice foiling and the difference of two squares formula give us the same exact answer. Last, let's use the difference of two squares formula for this problem here. I've started by copying down this exact original problem here, and the difference of two squares formula says, take this first quantity and square it, and then take this second quantity and square it, and then we put a minus sign in the middle. 6 squared will give us 36, and we could simplify this in a few different ways. One way is to apply the square to the 4 and to the square root of 3. 4 squared will give us 16, and then if we take the square root of 3 and square it, the square root and the square are inverse operations, they cancel each other out, so the square root of 3 squared just gives us 3. Or if you prefer to write this out, 4 square root of 3 squared is equivalent to 4 square root of 3 times 4 square root of 3. And we know that we multiply like quantities, so we would take the 4 times the 4 to get 16. The square root of 3 times the square root of 3 just gives us 3. And this is exactly what we wrote over here. This would leave us with 36 minus 48, which gives us -12. Again, the difference of two squares formula gave us the exact same answer as the FOIL method.